Hello, this is Spencer Snolling from Hydromantis, and I'd like to welcome you to today's webinar where we are going to be discussing inorganic precipitation and how we go about modeling that in our wastewater treatment package GPSX. My name is Spencer Snolling, and I'm Vice President of Product Development here at Hydromantis, and I'm one of the main developers of GPSX, and I'm glad that you're able to join us today. It will be a bit of a somewhat unusual webinar in the sense that we won't be talking about COD and BOD and all the usual things that we discuss in terms of wastewater. This will be talking about the rather equally important aspects of water chemistry, and in particular looking at the elements of the Mantis 2 biological model that relate to the inorganic part of wastewater, to looking at calcium and magnesium and so on, and how they contribute to the calculation of pH, and then subsequently from that, how that affects the precipitation of inorganic materials throughout your wastewater treatment plant, and that's an important aspect of many of the new features that we've added to GPSX over the last 5 years or so. So my plan for today is to talk a little bit about inorganics in activated sludge modeling and sort of the history of how we got to where we are now. I'll talk about more specifically the Mantis 2 model and how we've implemented it in GPSX, and there's kind of a couple parts to this. I'll talk about the state variables that we have. I'll talk about the processes that we use to calculate pH, and then subsequently precipitation as well. And I'll talk about a few of the relevant unit processes that we have. By that I mean the icons that you put on your drawing board, and how they are used, and how some of them are have particular aspects with respect to the inorganics that we've added in the most recent developments of our model. So as part of that, we'll be discussing how we go about calculating pH and precipitation. And as usual, I will run a couple of examples from my desktop here, run them live, that show you some of the pH calculations, show you an example where we will be precipitating out struvite in a digester, and taking a look at how that is sensitive to some of the process model parameters. And as always, if you have any questions, please feel free to type them into the questions box in your GoToWebinar dashboard, and I can see them popping up here on my computer. I'll basically go through the whole presentation and demonstration today, and I'll be able to see you typing in your questions. And then at the end, I will stay for another 5 or 10 minutes and answer any questions that you have at that time. Okay, so let's start at the beginning. Basically, as you all know, activated sludge model number 1 was sort of the beginning point for this, very detailed type of numerical simulation of wastewater treatment plants that we all do. So here's that original report from IWPRC. The original ASM1 model really didn't address inorganic components at all. It doesn't have any state variables for things like magnesium or calcium. And in fact, it didn't even have any sort of state variable at all to calculate for anything that wasn't organic. So if you take a look at the matrix for that model, and I realize this is a little tough to read with the small font and so on, but all of these components that are listed across the top here, they're all the various forms of carbon and nitrogen, but and then also alkalinity, but they didn't really look at including any of the inorganic stuff. So for that reason, the older versions of GPSX, and by older I mean sort of version 3 and earlier than that, had to sort of account for different ways to deal with being able to include the ISS, the inorganic part, into the suspended solids calculations, because everything that ASM1 did really only got you up to total COD, and it didn't take you to the next step to get to TSS. So in those old versions, and just for fun, I dug up a screenshot of excuse me, GPSX 3.0. That's what it looked like when I first joined Hydromantis about 15, almost 16 years ago now. In this version, what we used to do was that we would calculate and do the integration and mass balances on the COD and all of those state variables throughout the plant. But since there was no inorganic solids that were kept track of, we assumed a VSS to TSS ratio for various points in the plant. And then so we could use the conventional method of getting from particulate COD to VSS, and then we made another assumption about VSS to TSS, and that got us to our final number. So starting with version 4.0 of GPSX, we actually added a proper new state variable called XII, which is particulate inert inorganics. And it's a bit of a catch-all variable in the older, simpler models. You know, any sort of fines and silt and precipitates and basically anything else that settles out that doesn't have any COD in it, that falls under this particular category. So we treat it like a state variable, just like we do all the other ones in the model. You will find it in your influent. We calculate what it is based on the VSS and TSS numbers that you provide for us. And we do full mass balance on it. And it obviously does not transform in any way biologically, but it does settle out, of course, and it becomes part of the mixed liquor that you have, and you can plot its concentration throughout the plant. And, of course, we add it to the VSS number that we get and to get TSS. And if you open up the state variable menu for any one of the connection points in your layout, you will find that it's actually listed for most cases right at the very top there. Inert inorganic suspended solids. You'll notice here that it has a units of milligrams per liter, not COD, of course. So here for this particulate inert organic material, this has some COD. You notice it has different units. So just so that you're aware that that's there. Okay, now moving forward in time, about 7 or 8 years, to get to ASM2 and subsequently ASM2D. This was the first time in which the development of these models has taken into account state variables specifically for inorganic materials. So there was XMeOH and XMEP, which are the metal hydroxides and metal phosphate that are part of the ASM2D model. And of course, this was developed primarily to sort of introduce methodologies for us to be able to include you know, the use of iron to remove phosphorus, and so those state variables became part of that model. And in the activated sludge matrix, or pardon me, the model matrix, there are rates for consumption and generation of these two particular units. So they're kind of accounted for along the way. ASM2D, just by interest's sake, also had a TSS state variable, which was a bit of a different approach than what we do these days. And it had appropriate stoichiometry to relate it to all of the other elements, all of the other state variables in the model, and it got integrated as it went to and from throughout the plant. But we don't use that methodology. We actually calculate total suspended solids and you know, the VSS and various other things. We do that through the composite variable calculation that gets us from the state variables, which are in COD, into TSS. Right. Okay. So moving forward again, about another 15. No, I guess about yeah, about 15 years or so to get forward to the time when we released GPSX version 6. That was the point in the history of Hydromantis when we introduced Mantis 2. That's our most sort of comprehensive and advanced biological model, and the one that we continue to work on all the time. That was released in the fall of 2010 in GPSX version 6.0, and it sort of implemented a brand new way of doing all of this inert stuff that we had previously only done in various bits and pieces in the digester and a couple other places. It now became integrated with the biological model throughout the plant. So these are now calculations that are being done throughout the entire system, and that was one of the advantages of going to the overall sort of supermodel concept of Mantis 2. So we now have a number of new state variables, or state variables that are designed specifically for handling the inorganic compounds, both soluble and particulate, and I'll show you some more detail on those in a moment. And in addition to that, we then put the precipitation and dissolution rates into the biological model matrix, so that's now there, and anytime it goes through a biological reactor or any of the other places in the overall in your plant, you know, you can have the opportunity to have precipitation or redissolution if it's going in the other direction. And there are a few other places as well where we do metal addition and so on. Once that's in the stream, we can then go through a full water chemistry analysis of what's going on there. We can speciate all of those things out that for those compounds that dissociate. We can then use all that information to be able to do a calculation of what the pH is going to be at all points throughout the plant. And then we started in subsequent years after that to start to add in a number of new models and new unit processes that focus specifically on inorganic removal. So just to highlight those soluble inorganic state variables that are part of the Mantis 2 model. Now, if you open up a state variable menu at any stream connection point in the layout, you can slide down. This is sort of towards the bottom of the menu. You can find soluble inorganic compounds, and there's inorganic carbon. This is part of the bicarbonate system that is going to be solved throughout the entire plant. And then we have all of these other cations that are here, and we have some generic cations and anions that are also part of that system. Now, for the particulate side that we have, it's basically this sort of generic inorganic inert particulate. Those are similar to what I had showed you on that earlier slide. But now you can see that we have listed all of these precipitates explicitly, so we can calculate them and differentiate between them and be able to model them correctly so that they will precipitate out when the relevant constituent components are present, and the conditions in terms of temperature and pH and HRT and all that kind of stuff is relevant and in the right position. Then these things will start to precipitate out in the stream, and these are obviously a solid, so they can be settled out and removed accordingly. Okay, so as I mentioned, there are a number of different places where, when I say places, points in your wastewater treatment plant model where inorganic compounds are converted from one thing to another. So as I mentioned, we do precipitation and dissolution as part of the biological matrix. There are a few additional parts to this as well. Any place that you see this object, which is the inline chemical dosage object, that's where we can be adding metals to be able to precipitate out phosphorus and do other things. That's going to be part of where you'll be able to see the chemistry change. And then any one of the bioreactors, they of course are also ones where you will see some changes to your water chemistry and changes to pH and so on, because we are taking up some of those elements, such as calcium and magnesium and so on, for the growth of the biomass. And when we have death, they get released back to the system as well. And then, of course, we also have changes to the other concentrations that are going on which affects the pH, and then sometimes we can even link the pH back to inhibit the bioreactors and so on. So there's a lot going on in these particular systems as well, and this is where you would find precipitation of various types of precipitates in your plant. And of course the digesters too. It's basically the same biological model in this digester as in these regular bioreactors as well. I'll also very briefly mention, for example, this trickling filter and so on. It's the exact same model working in the biofilm models as it is in the regular suspended growth. Okay, so that's where all of the various conversions are happening. So that's the things that are sort of the chemical reactions going on. Now, there are a number of unit processes where the inorganic compounds actually are treated differently than the other solids. So in all of the clarifier models that we have in the Mantis 2 library, you'll note that in the settling parameters menu, way down at the bottom there, you can actually adjust the settling for each individual state variable. And this allows you to, if you like, to have the things that are like, the chemical precipitates settle out faster than the biological material. And now we don't do that by default. I think by default they all settle at the same rate. But what you can do, though, is have those things settle out a little faster if you want. And occasionally I've had to do that for a few projects I've worked on where there was significant, inorganic material that did have a little heavier, settled out a little faster, and we were able to calibrate the model as well. So we'll also note that the new object that we added in the most recent version of GPSX for drum microscreens also is designed to be able to differentially do solid separation and separate out at different rates the biological versus the chemical and the inert materials as well. So that's another one where you'll find a different way to separate out preferentially the inorganic material. And then lastly, we have our struvite recovery unit, and that's basically a combination of the two previous slides. We have the biological part and the chemical part, where we're actually using up and making changes to the concentrations of things like ammonia and phosphorus and so on. And then we have the presence of all of those inorganic materials, your ions and anions and so on. And then we have solid separation in here as well. So that's the one unit that was deliberately designed to help us take advantage of that Mantis 2 biological model sophistication to the greatest extent. Okay, so how do we go about calculating this? This is where we get down to the actual nitty-gritty equations here. There's actually quite a lot going on in the background when you are including pH calculation and precipitation equations in your model. So first of all, we've got to, as we do with all the biological models, keep track of all of the concentrations of all of the components. So things like ammonia and phosphorus and your BOD and COD and biomass and so on. So that's all going on like it normally would. And then on top of that, you've got a few extra reactions going on in your biological model that will be there to make sure that it keeps track of the consumption and release of some of these inorganic components when you have growth and death of your biomass. So those new components that we added with Mantis 2 are now being sort of incorporated into the regular growth and death equations. And then on top of that, we are also generating and dissolving those new precipitates as well, and that's all part of that matrix. So those things are happening. If the condition is right, if you have the right temperature and pH and so on, and your solubility is such that it's ready to fall out of solution, then it will do that as part of the biological calculations. Okay, so now we've got all of those in place and we understand how they all fit together. We then have the speciation calculation. So in every place where we know what the concentration of something like ammonia is, we can actually figure out what fraction of it is the ionized form. And then we can do a pH calculation on top of that. So that is a lot of calculation that's going on. So there is actually an entirely separate solver incorporated into GPSX just to do the pH part. And that's there to try and make things as efficient. Certainly there's a lot more calculations going on. You may have noticed that when you run Mantis 2, it runs a little slower than the other models. It's purely because there's so many more calculations going on and a lot more sophistication in the model itself. The cool part, and the part that makes this a valuable exercise, is that these things are often dependent on each other. If you have more nitrification, you may have a little, less ammonia, and that's going to affect the pH a little bit, which will then affect the precipitation a little bit, which will then give you maybe a little bit different solids. And, these things are all sort of tied together, and especially when you try to bring it all back in with including some pH inhibition in there as well. Okay, so as I mentioned, we have in the Mantis 2 model this uptake and release of the inorganic components like calcium and magnesium as part of the growth and death process, and we have a stoichiometry all worked out for what that would be. And it does make for a very sort of valuable part of the BioP removal system, because you can actually use some plots of the concentrations of calcium and magnesium as you look down the length of that plug flow system and see how it's taken up and released into various zones, and that's sort of an interesting aspect to be able to plot. And in each case here, we are looking at developing up a full understanding of what all of the ionized or what all of the charged concentrations are in this system in order to be able to do a prediction of the pH. So we essentially have this acid-base system, and we have many different components. And I'm showing you a few here. It kind of depends on what is the relevant species in any particular part of the plant. But most of the ones that are relevant for the most part are the carbonate system here, which dissociates to HCO3- and CO3 and so on. And then the phosphate and ammonia, also dissociate and give up H+ ions as we move along. Acetic acid, propionic acid, those kinds of things also dissociate and play a role in the pH calculation as well. And then as we've moved on to more advanced modeling of the nitrogen side, and particularly the nitrification and denitrification. We even get even more different types of and more steps in our nitrification and denitrification process. Some of those are relevant to the pH calculation too. So this list could potentially be even longer than what I'm showing you there. But just to give you a sort of a rough instruction of how we go about calculating that, I'm going to take a few of these elements and show you how we do the charge balance equation. So that's the way what we do is we know what the concentrations of many of these things are, but we need to do a speciation first and then a charge balance second to figure out where the pH would have to be in order to have electroneutrality. So when we have, just to run through a very simple example for ammonia here, we can see losing the H plus ion and then getting to NH3. This, you can write a chemical relationship like this for sort of any type of dissociation. You can write an equilibrium constant, and you put the product of the molar concentrations of the products over the, yeah, that's right, the products over the reactant there, and then what you get is a relationship that allows you to determine what the concentrations of these things are, knowing what your equilibrium constant is. So we have all of this kind of already built into GPSX, and these things like the equilibrium constant are all temperature dependent and so on. So we can use those and substitute those into more sophisticated equations in order to come up with a charge balance. So just to refresh your memory on how electroneutrality works, basically if you have all these charged species floating around in the water, they all have to have all of their charges total up to 0. Otherwise, you would have a free current roaming around in there, which we know doesn't happen. So what you can do is, since they all have to add up to 0, we can use that to solve for the things that we don't know. So now in many cases, we're going to have the total, when I say total concentration, I mean the free and ionized versions of these things. And then we can use the speciation calculations to figure out what those individual parts are. And then we can throw in the dissociation of water into H plus and OH minus into the mix, and then solve for 0, essentially. So that kind of looks like this. You got H plus all the other positively charged elements, and OH minus and all the other minus charged elements, negatively charged elements. And just to note the nomenclature here, these square brackets are looking at the molar concentration, because really what we're balancing here is charge. So it's in moles per liter times the charge for that particular cation or anion. So just to list down all the anions here for typical in most of the models that we're using here, we can see sodium and potassium, calcium, magnesium, and so on. And you'll note here that for these ones that have a 2 plus charge, that we multiply by 2 out in front because we have twice as much charge on those ones. And then the anions here, just listing off a bunch of these. And again, here for phosphate, we can see we've got a 3 in front. And then, of course, the dissociation of water. And then we substitute all these equations into each other and solve for H plus. And then that will, of course, give us what the pH is. So there's a lot of moving parts in this calculation here. And, of course, as we go through the plant and as things change dynamically, say you were running a simulation where the charge where the concentrations went up and down during the day, these concentrations of things like ammonia and potentially the acids and other things would certainly change as things went up and down and the temperature went up and down. So it has been quite a mathematical challenge to be able to pull all that together and get it to solve reliably and robustly and not slow the entire works down. Okay. I will mention as a sidebar here that we also, once we know the pH, we can then calculate the alkalinity, because of course we have still the dissolved carbon dioxide and the rest of the carbonate system that we can work from. And since we know the pH, we know what all the charged components are, and we can pick out the acid sort of neutralizing components and calculate that for you. You can find all of that if you want to plot it on the graph somewhere. By going to our output variables menu and down to the pH and alkalinity menu, which looks like this, and you can see a estimated pH here, and you can see the carbonate alkalinity and total alkalinity plotted down below, and these are going to be always shown in, most people don't like to work in moles off the top of their head, so we list them in and convert them over to milligrams as calcium carbonate. Okay. So that's the pH. We had to do that part first before we could get to the precipitation part, which is basically looking at these equations that we've now inserted for doing the precipitation of these various components of solution and become solid. So we can see here these are all the ones that we currently are doing, and we've kind of added to this list over the time, but it's the one down here at the bottom, magnesium ammonium phosphate, which is struvite, which is the thing that most people are worried about, is that it can easily fall out of solution and precipitate itself onto the inside of pipes, which then gives you a very considerable capital expenditure to be able to, a maintenance expenditure to be able to keep that under control, or indeed may have to be placed down the road. So we put those equations and take this approach by creating a new rate in the model that sits in there alongside all of the other biological rates like growth and death and hydrolysis and whatnot. And this is a rate for struvite precipitation, for example. There's a rate constant that, and of course these precipitation reactions are very fast compared to the rate of the biological components. And we are looking at multiplying. We're doing this as a solubility calculation. It's just like the equilibrium one that I showed you earlier. You multiply the concentrations together, and then in this case, we're using it as a driving force to be able to determine whether something is going to be in or out of solution. So if you have a lot of this in solution, and we compare it to the solubility of that particular component, then that will drive more things to be, precipitated out. And of course, this allows us to go. This one rate goes both directions, allowing us to either precipitate out or let stuff go back into solution again, depending on whether one's concentration is higher or the other. So we're modeling this as a completely reversible reaction. Okay, so that was a whole lot of talking and stuff. Let's actually do something a little more interesting by looking at some simulations. So what I'm going to do here is show you three very quick simulations that kind of cover off the pH part and then the precipitation part after that. So first of all, I want to go to some of these examples that you can see for yourself. Going to the sample layouts menu. This is what the sample layouts menu looks like in the new version of GPSX. We've reorganized this now. If we go to process analysis examples, there's a couple of pH things here. And first of all, I'm just going to do a titration example just to give you a feel for how that equation that I just showed you behaves when we do a titration. And so this base solution is essentially, it's not wastewater at all. This is just a reactor that is full of, a bunch of anions, a bunch of cations, and then we are now going to be adding in some anions to it in a titration. This is like 1 liter. We're going to add in a few milliliters as we go along. And we can see here as we went forward with that solution of the model that, the pH started way up here because it was a very basic, and then it kind of, as we added that acid, the pH here at the break point came down and so on, and we can see that that's a straightforward type of titration curve that you would expect to see, given the very simple system that we have here. Okay, so that's just a pure titration, very simple and straightforward. I'd like to go back to that same menu again, process analysis example, and do this pH control during nitrification. Now this is relevant, of course, because nitrification can take up a lot of alkalinity in your system, and if it takes up too much, then you can, not necessarily, but you can suffer from changes in your pH. So we've set up this example here. When I run it by default, what's going to happen is the influent ammonia is going to go way up and down here, and it goes from 25 up to 45 and back down again. And while that simulation was happening, we were, of course, estimating pH and so on as we do. And this is a fully nitrifying plant. And we can see here that this pH that starts at 7.2 at the beginning of the simulation actually does dip down to about 6.6 while that peak was sort of traveling through the plant. And, that does have an effect. So just to show you how the pH can be actually modeled and reflect the things that are going on in the plant, I'm going to flip to a scenario here where we're just putting in alkali solution. That's what this object is right here with the little blue container. And if I go to the feed chemical details, we can see here we're adding sodium hydroxide in this particular case. And we're just going to do that at a constant rate. There's no dynamic controller here. We're just going to let that move forward. You can see the dosage actually up here, this black line, constant straight across. And if I go back and take a look at that same situation again, now the pH is, much higher. And so it starts at 7.5 almost and drops down to 7.2. Basically we're just moving that up because we're adding, that hydroxide into the system. So now that might not necessarily be the best way to control the pH at your plant. What we can do is even use a controller. So if I go in here to this flow controller menu, we can see that we have a pH controller already set up here. I'm going to flip over to a scenario where that's been turned on and had the tuning constants filled in and so on. And right now we're going to try to control that pH to a value of 7. Now, of course, this is a real dynamic controller, meaning that it waits until the pH here has an effect before it turns on this upstream pump. But when we do that run again, we can see how it has an effect here. So instead of having a flat line of continuous dosage here, it didn't do anything for a little while, and then suddenly when that pH started to dip down here, just below 7, that pump came on, and it started to add that sodium hydroxide as was needed, and then as it came back up again, it turned it back off. So, those are the kind of things that you can do with pH modeling in GPSX, and in particular, it's very interesting for doing dynamics as the hydraulics of the system are taken into account here. There's the recycle, and we can see how this peak lagged behind this peak, and also the temperature effects and the concentration effects as things move around and change throughout the day. Okay, on to my third example here. So now I've covered off pH. I'm going to move on to an example where we are precipitating out struvite. So this is a very simple model that is starting with just the activated sludge portion of a plant. We got some primary effluent coming into a conventional activated sludge plug flow tank, and we're taking that waste sludge off and dewatering it, or somehow concentrating it up and putting it in our digester. So let's just run this. I'm only going to do steady state on this particular example here. And what we can see is this is a fully nitrifying system. If I look at the plug flow tank, we can see our mixed liquor here. We can see the ammonia comes in at 25 and goes all the way down to 0.13. And I want to go over and look at the digester here. The digester is producing some gas, and it's doing 50% VSS destruction, so it's kind of more or less doing its job. And I made another little table here just to sort of highlight the relevant part of the struvite discussion here. Basically, I listed these 3 things that are coming in. This is what's coming into the digester here. We can look at our ammonia, our phosphorus, and our magnesium concentrations, and we can see what the pH is in the digester. What the pH is coming into the digester. And we can see that those were all of the right situations to precipitate out 1,250 milligrams per liter of struvite in that system. So now it remains completely mixed while it's in the digester, but once it comes out, you can do solid separation on it or what have you. So this is all completely a function of the biological model that's going on in here and the constituent compounds coming in and their concentrations that were predicted by the rest of the model. So any one of a number of different things could have a huge effect on the precipitation, but I'm just going to play with temperature. Now this is the whole temperature around the entire plant. This is going to, of course, have an effect on the this portion of the plant here. And so we are going to affect the nitrification in this case. So I'm turning the temperature way down here. And what's going to happen, this could take a little while to sort of get converged here. But what's going to happen is if I'm turning that temperature, we're going to be dialing back the level of nitrification. So we're going to have more ammonia in the effluent here, and the more ammonia going to that digester. And we can see that given everything else being the same, that this also has now, by the way, of course, affected the solubility, and it has affected the dissociation constants and all of the other water chemistry important parameters. And we can see now here we're actually generating more struvite coming out of that digester because there was more ammonia. Apparently, in this example that I made here, ammonia was one of the limiting factors. And if I pump that all the way up to a really hot temperature, and we can get some another example now where this was previous when we ran it at 20, it was at 1250, and then we got it all the way up to 1300. We're now all taking it down to about 1200. So that's an example, very simple. You can change these process parameters. You can change the concentrations and the basic makeup of that sludge and see how that would go. You can change the size and temperature of the digester and see how that would affect your system as well. All of those things are relevant to being able to predict the concentration of struvite in your system. Okay, moving on. A few other last-minute thoughts here. There's a few other features that are part of this pH model that I'll just mention here very briefly. One of them is that occasionally, as I mentioned, having the pH in there really kind of makes it quite a lot more complex model. And sometimes it starts to cause it to be very slow or have a convergence issues or something like that. If you find that it's bogging you down and you don't really care about the pH, you're just going to assume the pH is fine, you can actually turn off the pH calculations by coming to this new button right here. This is the Site Properties button. We've moved a lot of the information that had been spread across several menus about the properties of the site, the temperature, elevation above sea level. One of them is pH. We've moved that into here. If you press that button, you get this menu. And there's estimate pH or set pH, and you can just type in what you want the pH to be. I'll also note here, too, in this model reactions menu just down below, you can actually turn on or off the precipitation as well, if you like. And lastly, I'll mention that we do have, and people have been asking for this for quite a number of years, terms in our biological growth equations that make the biomass sensitive to pH. And we did a webinar on the details of the Mantis 2 biological model about 6 months ago that talks about this in quite a bit more detail that I can show you here today. But we included the pH inhibition in the biomass by putting in another term that we multiply every one of the growth rate terms by. And it's something that ranges between 0 and 1. So first of all, I'll mention that this is turned off by default, and if you wish to turn on the pH inhibition, you come by right-clicking in the background here, selecting System Input Parameters, and then the pH inhibition menu here. And this function, this inhibition term, is most of the time equal to 1. When you're in a pH here, a range, this term is equal to 1 between, say, 6.5 and 8.5 or something like that. There's a boundary that you specify that it's equal to 1, and there's essentially no effects from the pH. Then, when you get to this boundary where the pH starts to become an issue, say we're getting below 6.5, you can specify the point at which you're down to 50% of the activity, and then we calculate a straight line slope here, and then same thing on the other side. You can say, I know this is the point when it is partly impacted, this is the point when it's running at 50%, and then of course we do go all the way down to 0. So we have established default values for these types of inhibition terms that are part of GPSX. As I said, the inhibition is turned off by default because it does give you, yet one more thing to be able to have to think about and calibrate when you're putting your model together. So we've left that off until you're ready to turn it on and use it. Okay, a few final thoughts. Mantis 2 is basically the model where you want to be using if you want to be able to do this level of pH and inorganic precipitation as well. It has a sophisticated approach to doing the water chemistry, more so than any of the other models that we have. You can use these models to assess the effect of how the biological activity is going to impact the pH, and also the chemical precipitation and other effects that are going on. The most common usage of it, what I see most people using it for in their projects is, this is when people want to dive in and understand when am I going to get struvite and how much am I going to get. But because of that, it does require you to put some extra information into the model, in particular, putting it right in there, putting it in the influent. We do need things like influent magnesium concentration and so on.